higher speed communications is extremely important in the data center. And one way to get that is fiber optics. But one of the challenges is the lasers. So can you tell us a little bit about your company and how you're approaching this challenge?
Yeah, so you're absolutely right. In terms of communicating between GPUs and memories, which is the key bottleneck that is currently there in the industry, using fiber optics has been a preferred platform of choice, especially using silicon photonics, which is leveraging CMOS platform for integrating optical devices on a wafer scale that can seamlessly integrate with GPUs and memory devices. But what has happened is with the traditional incumbent technology, the lasers that are currently used in data center application can only are basically fabricated using 3-5 foundries that are based on either indium phosphide or gallium arsenide, and they are typically on like 3-inch platform. What has that resulted in is a capacity limitation when it comes to scaling the number of wavelengths that you can use, that you can emit from a single laser. Today, the industry uses like 4 wavelengths. That is the maximum number of wavelengths that they can get from that can be integrated inside a single fiber optic transceiver, mainly because the economy of scale doesn't let them go beyond 4 wavelengths. What that translates to is a limitation on the maximum capacity of bandwidth that you can encode in a single fiber, and thereby limiting, forcing the industry to pursue other ways of like maximizing the bandwidth, which is either increase electrical interface speed, like basically pursue like 200 gig SerDes, 400 gig SerDes, looking into the future, and thereby again resulting in higher and higher power consuming alternatives. Right? What we have done is we have leaned on silicon photonics, which is essentially the platform of choice for these high volume application, and we have essentially come up with a solution where we use the silicon photonics platform to generate up to 100 wavelengths from a single device. And this technology is called, it's essentially based on comb laser technology that came out of Columbia University, and we've put our own secret sauce in it, and we've called it ChromX laser at Xscape, where we can generate anywhere between 4 to 16 colors with extremely high power for every wavelength that we generate, and thereby enabling the industry to immediately scale the number of channels that they can encode into a single fiber by 4x, and have developing a platform that can essentially like scale up to 25x the bandwidth on a single fiber at the same exact channel rate that the industry is currently deploying.
Now, I noticed in the oscilloscope display that the consistency between the channels was very high.
That is the biggest differentiation of our approach. Traditional comb laser technologies suffer from channel to channel variation that ends up making it unviable for fiber optic communication. And there are other alternate solutions, and the comb laser technology has been something that has been in an area of research for over 20 years, and every solution that is out there basically has almost like a sinusoidal profile, where the channel to channel variation is so high, making it extremely difficult for the receiver electronics and transmitter electronics to process the data on it without resulting in significant errors in the data. What we have arrived upon, and that's the Xscape secret sauce of ChromX laser technology, is essentially enabling a very high uniformity between various channels, so that the power variation across the channel is almost like identical, close to zero, and the spacing between them is guaranteed to almost gigahertz accuracy. What that really means is, just to provide you where the industry state of the art is, it's anywhere like the channel variation between multiple wavelengths can be anywhere between 50 to 100 gigahertz, the state of the art system. And we've basically reduced that variation to 1 gigahertz. And that's order of like almost like 50x improvement in the state of the art. and that simplifies the system design, reducing the number of overhead that you need in terms of like the control electronics and the way you design the system, and it simplifies the system design to a level where the power and the cost savings become valuable for the end customer.
Now, on the demo system you have, it looks like it's a pluggable module that would then drive a single fiber.
That's absolutely right. The current state-of-the-art systems that are out there in the industry traditionally uses a pluggable form factor to not only uh, embed the laser, but they also use it for like transmitting, like converting electrical to optical data and these are the optical transceivers that are pluggable in a faceplate. Now the industry is moving towards different architectures where they have taken the electro-optical and optoelectrical conversion on a silicon photonic chiplet that gets integrated closer to a GPU or an XPU or a switch silicon. But they have kept the laser, basically, which is the power source for these, remote, so that they can make it field swappable and make it interoperable with existing ecosystem. And the reason for that is lasers are notorious for like failing over time in terms of reliability, and the architecture should render themselves for field replaceability over time without actually taking down the entire systems. Right? And our solution, we are kind of first targeting that implementation where we are providing an external laser power source that will power these optical transceivers that would get integrated with these GPUs and the switches that are getting deployed in hyperscale.
Well, great. Thanks for filling us in on your advanced laser technology.
Thank you. Thanks a lot.